So, welcome to the lecture Cryptography, and today we are approaching the highlight of his courses, or the reason why I'm giving this course. And maybe I'm giving the course for the last time ever, because I heard that professorship that there's a new list for professorship of security, and maybe somebody else fills this post, and I don't have to. Probably he will be better expert than me doing cryptography. Okay, so what we are doing here, we are interested in zero knowledge proofs, and we started with perfect zero knowledge proofs for showing that you know the logarithms of a number. So let's see. So we are looking at. We start with perfect zero knowledge, and then we moved in and said, okay, maybe we don't need this kind of perfect zero knowledge, and some other is good. So we have this perfect. Last time we had this perfect zero knowledge proof that we know some kind of discrete logarithm. So this was a proof which was that we commit ourselves to some. So now we want to prove that we know x in this logarithm, and the protocol was that we have some commitment of some random number, and then we have a bit where we set 0 or 1, and then we send this B, which is the kind of sigma protocol, which we see very often. It's called sigma protocol because the arrows look like a sigma. That's the reason why they call this sigma protocol, because it has the idea that you commit yourself to some random value when you get a challenge, and then you give away half of the information. So this can be done much better in the sense of higher probability, because here you can cheat always with 50% probability, and you need the 50% probability of cheating from the prover side in order to make this perfect zero knowledge, intuitive level. Now, this was solved with Schnorr's identification protocol, where we have basically the same structure. We have, again, we want to show that we know this g to the x, and what we do is, again, we're committing ourselves to some random number. So this, no, it doesn't help. So this, just have to remove that, just a second. So we are committing ourselves again to this A. Now we get a challenge which is from a false space. So we have a challenge C, which is not 0, 1. And then we basically send the same answer. And then we check this equation. Now this is not clear how to emulate this protocol without knowing what is happening in the future, because a cheating verifier simulating here is very hard, because a verifier only knows A, and then it's hard to calculate all that. But if you look at this messages here, then this is statistically very close to perfect knowledge, and so we need an honest verifier, and then it's perfect zero knowledge, because then we can rely on random choice. Now, this was really a breakthrough with Schnorr's protocol, because before that, we had lots of zero knowledge protocols where you have lots of rounds to increase the probability from 1/2 to some very high value, and even then, it was not clear what is the probability that you need, and this all needs kind of lots of calculations. And for complicated protocol, it become harder and harder to make this in a feasible time with a small number of messages. Now, this is breakthrough because it's a constant round protocol, and you get a very high probability that this works, because you basically have to guess C in order to get A, and we have some kind of large prime number here, which makes sure that it works. So this is called honest verifier zero knowledge, and this also helps us when we replace the verifier with a hash function, because we have lots of choices. We can simulate the honest verifier with a hash function, which is not possible to do if it's just a bit. That was the exercise of last week. So we really need a wide range of possibilities in order to simulate a verifier with a hash function. And then we could actually do the same protocol and just have to check this one, but we got lost off the interaction. So that's why this is called a non-interactive zero-knowledge proof. Now, here you cannot really prove that this is secure, not even honest verifier zero-knowledge. But there are so many assumptions that we still assume that this will work quite well. Okay, so that's what we had. And starting with Schnorr's proof here, where we have this proof, a lot of zero-knowledge proofs came up. They can do lots, and lots of them have the same structure, like committing to a random number, then receiving a challenge, and then outputting a value which is dependent on the random number. So now this random number is now hidden somehow in this one-way function g to the r. And here now we are just revealing a random number which is secured by this one-way function. So the secret information x is, although it's challenged somehow, it's well hidden away. So you have no access to the secret information x because you commit only to this one-way function. So that is the basic idea. And as an example, last time we had to prove that we can now prove that now we have two generators here and we prove that they have the same exponent. Again, we commit to two random numbers and then we receive a challenge here and we do the same calculation and then we prove that it's the same. And this is not even honest verifier zero-knowledge. This is only computational hard because these two things are connected to each other. So you cannot simulate A1 and A2 without of course you could simulate it, but when you have problems to see B, and so in the end you would say that okay, nobody can distinguish that from some random distribution. Okay, lots of protocols we had here, and if you follow that, you could do some interesting things. You could prove multiplication. Now, what does this mean? Of course, we have lots of multiplication here because we multiply, but we are now talking about multiplication in the exponent. And multiplication in the exponent is that you have now three commitments. You have g to the a, you have g to the b, and now you want to prove that you know g to the a times b. So that means g to the a to the power of b. So that's similar to Diffie-Hellman, so where you have A, you have B, and then you need the secret to do this. Of course, the prover has access to all secrets, which is also some kind of limitation. So you need all the secrets in order to do the calculation. But how do you prove that this is a product of two numbers? And this is in principle the same way, but it's two Schnorr proofs combined. So we already have seen that we can prove that we know the same exponentiation. And so what we do is we do this twice. So we commit ourselves to some bunch of random numbers here, g to the r1, g to the r2. And now we also commit ourselves to g to the r times r2. So these are somehow connected here because we have the same random number, and we commit ourselves to g to the b times r1. And these are two connected because we're using the same random number. Okay, so this is something we need. So if a and b is not 0, then this is safe. Or if a and b are random numbers, then this is safe because you cannot see what kind of structure it has, which is something we will come back very soon. Now, so this is something which receives the verifier, and you see that in this protocols you get lots of variables. So what I do, this is just my notation. You don't have to follow it, and nobody else does it because I never published anything with that notation. Is that I want to see the structure inside of a formula, but still want to make clear that this is somehow hidden. So if I send this information, I write down on the verifier side that the verifier gets these kind of strange numbers, and they're in a box. Now I could make a black box, but black box has a disadvantage that we also don't see what's inside. But this gives us the immediate information that the verifier just gets here a bunch of numbers which may or may not relate it, and don't have to introduce new variables to show that. Okay, so from a verifier side, in this Schnorr-like protocol, we get this information. Then we get two challenges. And the two challenges are related to two things. One is for the multiplication with A, and the other one is for the multiplication with B. Because what we first do is we want to check that G is somehow multiplied to G to the A, and GB is somehow multiplied to G to the AB, but this is the same factor. And this is something, so we know which kind of factor achieves this multiplication. And this is which factor A, but we have this factor A, but we don't want to publish it. So we know the exponent which does this multiplication. And for this, we do the first half of this. So we take one of the challenges and send this information. And like in the proof, where we prove that we have the same exponent, we do the same thing. We use this challenge and the answer in order to prove that we get somehow from G, which is public, to G to the A, which is, we don't know what A is, and here we get also from G to the B to G to the AB. So that is the thing. So there is the same factor going from G to the A, and the same factor going from G to the B to G to the AB. But it's not clear that this is really the factor that we have here in the other commitment. It could be some other number. And so we do this twice, so that we prove that we know also the factor going from G to B, and this is the same factor as going from G to the A to G to the AB. Okay, so that now we are using this G to the A, where we have proof that this is somehow A times this factor, and we also know that this is somehow this factor A. So whatever factor we know here, which we call B, then this must be G to the AB. So that's the other approach, and for this we use the other challenge in order to prove this factor. So basically we are working on a triangle where we have 1, and we prove that 1 is multiplied by something to A, and B, which we don't know, it's B, but is multiplied to something like A times B. And then we prove that it's also happening in this direction, but this is also the same. And when we know it's A times B, because we prove that we know that this is a factor of B, and this is the same thing here. Okay, so why are we doing this? The idea is that if you have addition and you have multiplication, basically you can do arithmetics. So you can calculate things, and you do this in a hidden way in the exponent, and you can do this with a constant number of interactions. So that's the reason why we do something complicated like that. However, we are not really there at this moment, because this only works, this is only safe if A and B are random numbers. So there's not a lot of applications where you use random numbers, So you want to calculate the sum, the sum of our income, and I want to prove that I have a sum in a safe way. So you don't start with random numbers. Usually some of you have no income, so you have 0. And if you put 0 in this multiplication, just assume that A is equal to 0, just as an example. What you get here, you send R1. Yeah, so you send R1 times CA times 0. So you send R1. And when you can check, oh, this R1, I know this. You just send G to the R1. I just try out G to the R1 and I see, oh, this is G to the R1. And the only way is that A was 0. So you're giving away the information that A is 0. And if you guess, so this gives you, the same for B. B0 is something you cannot do at this moment. And you can also see that from some other constant choices, so that you start guessing around, that you can get some information out of this. So for example, assume that A is 1. If A is 1, you will see, this is the same number. Thank you for this information. So A must be 1. And then it's not safe anymore, or even some other constant choices. So, and if A is 1, then this is 1 also. So you have it right away. So you have some problems here with small numbers. And we want to do zero knowledge proofs for any number. That would be cool. And there's so this is one problem. We will solve this very quickly, but the other problem is also very critical, and it's hidden. Now later on, we want to commit to something like that. So sending a bunch of numbers is maybe tedious, and you don't want to do it, but you just want to have one number which commits to everything, like to A, to B, and to A times B. That's also something we want to do, which only works if you don't know the relationship between G1 and G2. Of course, they're somehow related. So that's something we have to do on next exercise still. But for each of these generators, which you use from the subgroup, there is a relationship that you can write it something like that. And if you know that, then you can cheat. For example, because you commit only to this sum in the exponent and not to the product, so you can change some other values A prime and B prime, where the product is not A times B. And this is the calculation to do it. So you can show that as long as you don't choose it like this way, you have to another A prime and B prime, where this kind of H2 and H3, where you actually get some other numbers which are not the product, although it's the same number. So we have to hide this information between generators, which is tricky. So how do you make sure that you don't know anything? So you have to how do you can prove that you know something, but there's no way to prove that you do not know something, because you can always play dumb. So, I don't know, I haven't seen this person in my life, So that's a problem that we have here. So, and there is an elegant way to do this, that somebody else gives you this number. So we need somebody else who gives us these generators, a trusted person. But so you get it from a server, from an NSA or something. Which is also not a solution, because we don't trust servers. The whole idea is that we make a zero knowledge proof so that we don't have a trusted person. If you have a trusted person, we could use as asymmetric key. We just use RSA, send it to the server, and the server does the rest for us. And we don't have to work with that. But we want to have this in one-to-one basis. So what we do is we emulate the server doing this by having a hash function. So we say, okay, let's do this hash function, start with a seed, and it produces some kind of H. And with this H, we have the entry to the ring. So we have this is now a pseudo-random H, and we compute the generator like that. And these are the 10 generators we have to work with. And if we need more, we just take the next output of a pseudo-random number generator, which we agree on that this has nothing to do with the kind of field we're working in. Okay, so you see that lots of mathematics and here some tricks in order to make it sure. But under the discrete logarithm assumption is that we should not get any information if we have this from a different source. So that's we don't know how it's related, because otherwise this hash function would somehow get a relationship for the discrete logarithms. So, and then generators are cheap, numerous, and safe. Never trust a generator which you haven't generated on your own. Yeah, so that's or you know how it's generated, because you cannot distinguish that from somebody who has the secret information somehow that generator 2 is some power of generator 1, because you just can use a random number stored somewhere and it looks exactly the same. You just have the secret information. And then you can break the schemes. This technique is called nothing up my sleeves, to make sure that this is a fair ground and we're playing this and we assume that this is the case as we assume that we're working with the GK. Okay, so much so, a lot of groundworks. And if we have as random generators, we can do something which are called hidden Petersen commitments. So we want to make sure that A may be even equal to 0, or A is equal to 5 or something. We want to commit to that value. So of course we cannot write down G to the 0, because that's spawn. That's a bad idea. So what we do is a so-called hiding commitment. So what we do is we have two nothing up my sleeve generators, and the first one has a random power, h to the r, and the second one is whatever we want to have it. Which is, by the way, the same way how El-Jamal works. El-Jamal uses the same encoding, that you have a generator to some random number multiplied with a message, and the message can be anything but 0. And 0 is no chance to get 0 because it's an exponentiation. So that's the same security as El-Jamal here in this point, that we hide it with some random number. So R must be random, but A can be anything. Yeah, and since we are already storing information in a number, we can store lots of information in one number. So we can take a whole array, and we have a set of generators, and pump it all into this number. And as long as the discrete logarithm assumption is true, there's no way to get another set of values which produce the same value, because otherwise you can compute the discrete logarithm. How do you call a function which maps large amounts of data into a small amount of data? Yeah, so which is secure. How would you call that? It's a hash function. Yeah, so this is a hash function basically. It's a hash function with where we can prove that something is put inside into this hash function. And well, not quite, because if you multiply that with h to the r, it's a random number multiplied with your hash function. So it's any number. So basically you have a random number where you can prove that this has a certain structure, but it's a completely random number. And it can contain an array of 20,000, size of 20,000 bits or something, with the generators which are related to each other. So this is mind-boggling that you can put this into one number as much as you want. The question is it any good? Because you squeeze everything in this number, and the next thing is, can we do efficient operations with that number? So that we can do, in one step, we can do something that is like a parallel computer, where we can do parallel operations with this representation. And this is what the lecture is about, that we now want to use this representation. Yeah. Yeah, this, without the h to the r, it's a hash function, because it's uniquely defined. And what you need for the hash function, we need that there's no collision. So if you can produce a collision, when you have two numbers where you know that this number relates to this number, so you have a relationship between the exponents. If you have a relationship between the exponents, you could somehow know that there's a linear relationship between the generators. And if you can make this consistently, you can get the exponents between two generators, which you didn't have before because we assumed that we didn't know that generator 2 is some power of generator 1. And that's why it's deterministic until you do the hiding. You have no collisions. You can efficiently construct because otherwise you can somehow compute relationships between the exponents. And yeah, so that's a hash function without this first factor. So, and you have a very small range where you map to. That's also the other thing that you need for hash functions. So, and that's a surprising thing. But we will, we don't use that as a hash function later on. Oh, that's a typo probably. Yeah, so that should be 2. Okay, that's an easy question. So probably I didn't have my glasses on when I copied this. Okay, but it's still a hash function. You have to twice everything. Then it's still a hash function because we just get 2 times E1, but it's not clear what happens inside. Okay, but I hope that I answered both of your questions now. Okay, on the bottom line is now we can use any numbers. Yes? R is the only random number here. So, and this random number makes everything random. It's random, but still, if you want to explain somebody else how you got this number, the only way you can do this is to say, okay, I have used this random number and this exponent, and that's the only way I get to this number. I don't know any other way. And if you forget these numbers, it's a random number for you after that. So that's a tricky thing about this hiding commitments. So it's not anymore a deterministic function where you end up with a product. It's just a random number. Yeah. So, and it has an internal structure which is only known to the person who made this random number. Yeah. So, yeah. That's typical for asymmetric cryptography, that you end up with this kind of things where you can say this doesn't make any sense. Okay, yeah? No, you need R, because if you forget about R, it's just a random number for you. So if you multiply with h to the r, you throw r away when everything is lost. It's a random number. I can prove that you have no way to access the information inside. Even if you know E1 to En, you cannot prove anything after that. So you need all the exponents, and you need to know this afterwards. Yeah, and you can prove that you know it just by showing it, which is something you don't want to do because that's the secret information. You don't want to show this. Okay. Okay, so with the hidden commitments, we can, first of all, we prove that we know it. That's just so what we do is we have this H and G, and we want to prove that this is somehow, I know the exponent, but I don't tell it to you. So I don't want to show this X and R, and it's still a secret. Okay, so what we do is, it's a typical Schnorr proof. So where we have this is given. So we choose 2 random numbers, and what we do is we do another hidden commitment with these 2 random numbers, R prime prime and R prime. Okay, and that's what we send. So we send another number which consists of H and G. Now we do a challenge again. So this is the challenge. And now we do the following. So after we got this challenge, what we have to do now is we send 2 factors. One is R prime plus C times X. So that's the secrets here somehow. And the other one is R plus C times R prime prime. Okay. For this, there are two things important. So B prime is secured by so this R prime prime here. So this is a random number from chosen here. So this R prime prime saves somehow the exponent from R. It's multiplied with a random number, and this R prime is also a new random number. So we have two random numbers which secure these two exponents we give away. Okay, let's check whether it works. So this is the old notation. So G to the, so here we do two things here. We prove that these are powers of two generators. So alone writing this in this presentation means that A and Y can only consist of two generators, which is G and H. Because if there's a third generator, then we have a problem. That's something, so then it's something wrong with generators. So that's the first thing, because you write this as G to the B and H to the B prime. You already know that this must be some product of two prime numbers. So let's see if I made a mistake. So what you have G to the B is R prime plus C times X. Okay, so that's what we check. So this is hidden for verifier. When you multiply it with H to the B prime, which is R plus C times R prime prime. Also hidden. And the other side, we have H to the power of R prime prime times, this is the A, so this is the A, G to the R prime. It's also hidden. And then we have Y, which is, Y is, original is H to the R times G to the X. And I hope that you can remove that thing here. No, it doesn't, it never works when you need it. So no. I hate this. I didn't have a course for multimedia, maybe. To the power of C, so this is to the power of C. So let's see. Okay, so I made a mistake because this is just the opposite way. So this is R times C. So G to the XC, that's correct, plus G this one. But for the hidden exponent, I made a mistake because this should be R and this should be R prime prime. Okay, so this is gone and this is R prime prime. Okay, that's why the other notation is much better, because here you can write anything, but here this makes sense. So going back, so this is secured by R prime, is something we have chosen this commitment at this position, and R prime prime is also something we have chosen. So we have proven with one challenge that we basically know that this is some power to the product of G to the B and G to the B prime. So we have proven that the internal structure is like that. We have not revealed any number because this number here is added by some random number, and the only thing that we reveal is the exponentiation of G to this random number, which should be safe because of a discrete logarithm assumption. And here we have R prime prime, and this is also hidden in this A, which is a random choice. So you get a random number which is somehow off to the real number from this exponent here. And what happens if x is equal to 0? If x is equal to 0, you would reveal R prime here. You would get this R prime because you could see it. But you cannot do anything with this R prime because it's G to the R prime. And you have here a random number multiplied with that. So basically, everything is hidden, and you can prove that this is the case. So this is not the proof for the correctness and soundness and whatever of this thing. This is just the intuition that you can gain from how you can hide this information. So, and that we can work with that, and we can prove the Zillinger property. Now we can do more things with that. We could say, okay, I can prove to you that here in this statement, A is equal to 5 or something. This, you could send R, you can send A, and when you have done. But this is something you do not want to do, because maybe the hiding exponent was used before. You don't want to reveal the hiding exponent. So what you do, but you want to reveal that it's 5. So you send 5 to the other person and to the verifier and say, okay, I take this hidden statement and I tell you it's G to the A. And so you say, okay, just compute that. So there's a mistake here. So receive G to the A. Oh, no, that's correct. Sorry. It's correct. So this is a comma, not the product. So on the other side, you get the commitment and you get A, which is not a secret anymore. And then you can calculate this. He computes that one. And then we have a Zillner-Notch proof that we know H to the R, which is exactly Schnorr's proof, that we know the exponent and it's still hidden. So this is basically proof that we can, for a hidden statement, we prove that this is a constant. Okay. We can also prove that it's an addition. This is easy. So what we do is we have these kind of 3 hidden statements here. And when you prove that A plus B is A plus B. Yeah, that's what we want to prove. These are the commitments. So here again, we can do the same trick. So we say, okay, you already have these 3 commitments. Now please multiply the first 2 and divide it by the third one. He does it, and the result is that he gets a new number. He doesn't know anything about this new number. But if this new number is just the exponent of H, then the hidden numbers here somehow have added up. Because I take the sum here, because by multiplication I have a sum in the exponent, and if I have a sum exponent and remove it, I get the information that this is the case, that this is somehow added up. Now maybe what is missing here is that you have to prove that these commitments are in the right form, that H, R, 1 and G to the A is in the correct form. Because it could be that there could be more information with some other exponents, and correct form means that this is something like H to some star and G to some star. That's something you should do in this protocol as well in order to prove that this is really the case. That's something I should add to the slide, that we have to prove that this has the correct form, because otherwise you could have some other generators which happen to add up as well. And they're just multiplied into that. So far, so easy. Now let's do multiplication. So for multiplication, we have to keep in mind that this was the proof about the multiplication here, which we probably didn't understand there. And getting hiding factors doesn't make it much easier at all, or just makes it more complicated. Okay, so the commitments are now hidden somehow. Everything is hidden here. And there are 3 different numbers which are hidden. So we need a bunch of random numbers. Basically, this goes now to 11. So, but it's constant. Yeah, that's a good thing. It's constant. But and we have to send a lot of commitments at the beginning to show that we're working that. And so we have to prove that these commitments are in the correct form. We don't need this for the first 4, but we could also do this for the first 4, that you don't have to bother about this anymore, that I and G RJ is something like h to the h star times g to the star, that this is this form. You can prove this too. So we don't have to bother about this anymore in the future, but the protocol does this automatically. Okay, so we know that all the commitments that we do at the beginning have the right form, that they are some kind product of h times g, or maybe even just powers of h, which is something here. So it's clear, but we don't know anything about the exponents after preparing all this. Now again, we have two challenges. One proves that it's multiplication with A, the other is proves that the multiplication with B. And this is basically the information which is most important here, because the other ones just adjust the hiding exponents. Okay, so what that's a prover. Verifier gets this information, it's all hidden. Basically, the verifier gets a bunch of numbers where we know what's going on, but the verifier doesn't know. And the first thing is, here again, the multiplication times A is what happens here, which is using the same exponent here. So we have this hidden commitment of g to the b, and we say this to the power of this exponent is the same as here is g to the ab at this position, and here we have g to the a. So that this is the same thing happening here. So this is a multiplication with a. Yeah, so we multiply somehow with a, and they are somehow related. Another thing that we show is that here in this first line, we represent everything as h, as powers of h and g. So there's no other generators involved. So h and g is public. So this is the proof of multiplication. And we have this commitment at the beginning, this one, g to the r4. And here, that's the same thing as before, g to the b times r4. And they're also hidden with some random numbers for this hiding coefficients. And we also have here, we have some factor h to the r8, which well, probably we could have omitted, but no, I'm actually not sure. We need this as well. And we could have added something here as well, because it's just, we prove that this is just a factor. And now we adjust this factor here. So these hiding factors are just adjusted that the equation is true. The same here for this one. You adjust with hiding factors. Now, the danger is, do we leak information? That's a thing, because we have some complicated equations here, and there's some easy way to check it. So here, for example, we have R4, and we commit to G to the R. So here somehow this changes. So this G to the R4 is somehow connected to this one. But this is a new random number, so this is safe. Here we have R10. R10 is only used once in this all equations. R10 is only used once. Here. R8 is also only used once, so basically probably was not necessary. I will see. So R8, so these are new random numbers which save for the expression. And here also R5 is also used once, and here it's hidden in this exponent. R6 is only used once, and R9 is only used once. Oh, no, R6 is also used here, and that's why we have to add a new number R7. So if you look at this equation system and you want to solve for this random exponents, it's not determined. So you don't get, you cannot simplify these equations in order to solve, oh, R4 is equal to 3 or something. So it's dependent on numbers which are hidden in this equation. So that's the reason why we have to add some, all these kind of hiding exponents here. On the bottom line is that first of all, we do the same trick by multiplying by A and here multiplying by B. We show that the first one is some power of G going this direction. So this is somehow, so we know that this must be some kind of factor G to the B and this G to the A, and all these H's are just kind of hiding. And now you know that since we have this g to the b here, and we have the same factor here, that we also have this in the form g to the ab, and some kind of hiding exponent we don't care. So the hiding exponents are completely unimportant. They're just random numbers that you have to adjust with random numbers in order to make these equations meet. So that's a technical thing about hiding things. And the bottom line is that the most important thing that you learn from this works somehow. Maybe there's some secret going on here, because later on we don't do the proofs for hiding commitments anymore, unless it comes automatically. But this is something you can do for multiplication, addition, and so on, and showing the constant. Okay, now we have to do a break, and then we show how to do this better.